Key theorems here. First of all, we have, I believe this is from Gromov's original paper, or one of the various expansions of Gromov's original paper. It is that if we have f is a map from x to y is a quasi-isometry between two hyperbolic spaces. Induces a mapping boundary. Which is a homeomorphism. Induces a map. A homeomorphism. Okay. All right, so the key thing here, so quasi-isometries induce homeomorphisms. In particular, the boundary, we can talk about the boundary of a hyperbolic group. All right, boundary G is well defined. Okay, so that was the key to this being useful for the point of view of geometric group theory. All right, so my question is the converse. Given a homeomorphism on the boundaries, what can I say? Does it necessarily come from a quasi-isometry? And that question is, well, there are a number of people involved, but let me quote in particular a theorem of Paulin, because that's the one we're going to be following today. And this was in 96. Paulin proved the following. So let's see, conditions, I guess, yeah, I need co-compact. So x, y, proper, and I will require co-compact hyperbolic spaces. Here I'm being vague about co-compact. I mean, there exists some co-compact group action on X, there exists some co-compact group action on Y, but we know nothing about the relation between those groups. We just that there's some kind of co-compactness.
Okay, is the co-compact group action proper itself?
I don't think we even need that, but I don't want to swear by that. But the important thing is I know nothing about these two groups. The groups are not related in any way, in any way. Just, we basically, I'll show you where we need the co-compactness. Okay. See. Okay. I think, it doesn't matter. So then, yeah. Oh, yeah, and suppose let's call it capital F, between boundary X and boundary Y, is a homeomorphism. And following are equivalent. 1, F is induced by a quasi-isometry. F is quasi-mobius. And 3, F is quasi-conform. I'll talk in a minute about what these are about. Let me just mention before I go into more detail here that I should probably put some other names. I thought some of these people might be ones, but I should probably put some other names here. Paulin's work was based on a lot of prior work of various people in the case of non-positively curved manifolds, homogeneous spaces, etc., etc. So some other names that ought to go in here for related work, well, Gromov, of course. There's Paulin. And somebody whose name I don't know how to pronounce. I'm probably missing some, but there's been a lot of similar work in other, slightly other contexts. This is the one I'm going to be following most closely, so I quoted this one. Okay, so let's go back and look at this theorem and see what it says. Okay. For today, I'm going to be focusing on this equivalence. I'm not going to say much about this, but I will make a comment about it at the end, and whether, I'm going to be trying to generalize this statement. All right? I'll say a few comments if I have time at the end about quasi-conformality. So let's focus on the quasi-mobius. So what does quasi-mobius mean? Well, if you've been going to Victor's talks in the afternoon, Victor Schroeder's talks, you've heard you've heard a lot about Mobius, about cross ratios and Mobiuses. But I'm going to define it. I don't know if everybody's been going to that, and just to motivate it. So let's define what quasi-mobius means. All right, so quasi-mobius has to do with cross ratios. So what's the cross ratio? So classically, cross ratio is defined for 4 points. I'm sorry, I put it in a funny order, but no, wrong. I did one. Yeah, I do want them in the right order on this one, sorry. Yeah. For 4 points on a projective line, and it was defined as follows. You take the distance from A to C, multiply it by the distance from B to D, and divide that by the distance from A to B, times the distance from C to D. Okay? All right, it turns out this has a lot to do with hyperbolic geometry. In fact, you can define the hyperbolic geometry in terms of cross ratios. The simplest case is the Klein model for hyperbolic space. So in the Klein model, if I want to define the distance function, so I don't know, most people are more familiar, of course, with the Planck wave disk model, but there is this model, the Klein model, whose geodesics, instead of being like this, like they are in the Planck wave disk model, are chords. The geodesics are chords, all right? And it's an equivalent model, it's just, so the Klein model, what's the distance between 2 points? Well, I'll call my points B and C, and I want to know the distance between these 2 points. Well, I just take the straight line, the chord that goes through B and C, call this A, call this D, and the distance between B and C is just defined to be 1/2 the log of this cross ratio, of the cross ratio. All right. So, all right, the key here is that a Mobius transformation, that is one that preserves hyperbolic distance, necessarily has to preserve cross ratios. All right, and vice versa. Okay, so Mobius. By the way, there is a definite. You can also describe the Planck wave disk metric in terms of cross ratios. It's just a little harder to draw the pictures. This one's very simple. So, all right. So Mobius map. So the point is Mobius transformations. Transformations preserve cross ratios. Okay, so that's all motivations. All right. So now let's define. We want to define a cross ratio on a more general hyperbolic metric space. In fact, on the metric space union its boundary. So we now want to take okay, so now we're back to X as just our general hyperbolic space, and we want to define a notion of cross ratio. Well, X union the boundary type, so we really want to extend it to the boundary. Right? All right, so I'm going to start with Paulin's definition and then tweak it a little bit. So let's start with 4 points, A, B, C, D. No longer have to be in a line, just any A, B, C, D. And let's start with the case where they're in the interior, and then we'll push this to the boundary. All right? So we'll define it like this, and it's sort of, you can sort of see how it's motivated by the definition up there. B, C, D. So this is Paulin's definition. Well, the one he uses, I think, was introduced originally by Tal, but anyway, this one he uses in his paper. To be 1/2 the distance from A to C plus the distance from B to B minus the distance from A to B minus the distance from C to D. Notice what's happened here is we've expanded this log into, you know, that log of that, minus log of that, log of that. You might ask where the logs have gone. Well, at the boundary, I'm hiding all this. The metrics are defined by exponentials, so when you take your logs, things disappear. Anyway, this was his definition, or just what it's motivated by this, okay? So we're gonna simply define it like this, all right? But I want to think of this a little differently, because we're in a hyperbolic space now. Let's draw a picture of this, all right? So we have now, where we've got 4 points, A, say B, B, C, D, any 4 points, anywhere like this. Okay, and wait, A, B, yes, I'm sorry, in my notation that I've been using, yeah, this is what I want. Hopefully I've done this right. We'll see in a minute if we've done this right. So I want to think of this sum in a different way. So let's connect A and D by a geodesic, and connect this. Hopefully I got my labels right. I'm not sure if I did. I keep changing them, and I think this is right. Okay. Now these are thin. We're in a hyperbolic space, so these are thin triangles, right? So how I want to think of these lengths like this. I want to take a projection, call this projection P, and take a projection and call this Q. The projection, the nearest point projection. Okay? The nearest point. All right. So in that case, what am I taking? I'm taking this length. So this is this length. I'm putting a plus on that. This is this length. And then I'm subtracting this length and this length. Yes? Okay? And taking half of that. All right? But the point is, this length is approximately this plus this. This length is approximately this plus this, etc. Right? So I can replacing these lengths by the lengths I get by going to the projection and up. Remember, delta hyperbolic means that these projections are very close to the length. This is approximately equal. In fact, it differs by, I don't know, something like at most 8 del. I mean, some fixed amount, 4 del. To exactly the distance between the projections. So for our purposes, because all we're going to care about is bounding the cross ratio up to some bounded amount, this is an easier way to think of what it is, rather than writing out these sums. It's easier for us to just think simply of taking the projections and computing the distance. The other reason it's easier to think about it is that this makes sense on the boundary. So if I let these points now all go to infinity, and I ask what's the cross ratio infinity, I can't talk about the distance between A and B anymore, but I can talk about the distance between the projections. All right? So, so define, so for, now A, B, C, D, on X union boundary X, we can define. For our purposes, we'll simply define A, B, C to be the distance, plus or minus, I should say. I'm only going to care about absolute values, but I can say what this means exactly. But PQ, where P is the projection on the geodesic from A to B, the A to D, B, and Q is the projection on the geodesic from A to B. Right. Yeah.
Okay. That's a little messy, right? P and Q aren't.
Yes.
They're just
P and Q are messy. So what do we really do? So you're saying, in other words, to what extent is the, so now I'm like this, right? I want to project, right? So the projection, actually, what you show is you look at all, sort of rays here, and they're, all the projections lie in some bounded set, and you take the barycenter of that set. So you make it a unique point. Or think of it as a little set, if you want. As I said, all I care is up to some bounded distance. But yeah, the easiest way is to define it as the barycenter of all the projections. Show that they're bounded. Okay, so you can do that. Yeah.
I was just curious if this is about the same as the one Victor defined in his class.
Well,
He also had a
defined
question.
using.
He had some different way of doing it.
Yeah,
But it's the same thing.
they're up to bounded. So
Okay, yeah.
he cares about things precisely. He wanted to preserve things precisely. So in that, so this is going to be the same up to bounded whatever of any of the definitions you can
Fine.
find in
Right.
anywhere. And as I said, we're going to only care up to quasi-mobius. Mobius means preserving
Sure.
on the nose. We're
I
only going
understand,
to care up to
sure.
quasi-mobius. So this one just works more easily from our point of view. And it's not what Paulin uses, by the way. Paulin actually just defines this and then talks about lim soups of sequences to lim inf of the soup of the lim infs of the sequences to go, points going to infinity. And we started out actually when we first started doing this theorem using that, and it's just a big mess. And then we realized that, it's just cleaner like this.
Yeah.
It's just cleaner and easier to think about like this. That's all. So, but yes, everything's really not unique, but we just take barycenters and it becomes well defined. All right, so this is a good way to think about it. All right, so now, so we now need to define quasi-mobius now. So boundary y, when these are both hyperbolic now. We'll say f is quasi-mobius if there exists a function infinity, and if you want, you could always take it to be continuous. In fact, if you take it to be non-increasing, if you want, you can take it to be a nice function if you want, such that for all x, the absolute value of f of b f of d is bounded by psi of a, c, d. Oh, you said that. Oh, I'm sorry. This should have been a homeomorphism. So take a homeomorphism. All right, start with a homeomorphism, or a bijection anyway. And similarly, so when we talk about it being quasi-mobius, we want it both directions. Quasi-mobius in both directions. So we have an f and an f inverse, and they both have a function. So there's some function that bounds in each direction. All right. Okay. So let's see. I've ignored the sign because I don't care. I'm always going to take absolute value, but you can define the sign here. It depends on whether P and Q are in this order or that order orientation. It really is irrelevant for what we're going to do. So okay, so that's the notion of quasi-mobius, and if we remember, let's see if it's still there. Here we go. So the claim is, if I have a homeomorphism, and what Paulin's theorem says is, if I have a homeomorphism and I know it's quasi-mobius, then it came from a quasi-isometry. All right? Well, both directions, but the forward direction is not hard to check. I mean, the 1 implies 2 is not hard to check. It's 2 implies 1 is the interesting part of this theorem. All right. So let's talk for a second about Paulin's proof. In particular, given such an f, how do I get back my little f? How do I get back my map on the interior? So all I'm given is a map on the boundary, and I need to get back a map on the interior. All right. So I'm spending a fair amount stuff that's known, because the other stuff I'll just say the same thing works, not quite, but it doesn't work quite the same way. But the ideas are already here, all right? Okay, so so given F quasi-mobius, how to construct. So the question is how to construct a map on the interiors. And then, of course, prove that it's quasi-isometry, all right? Okay, so here's the idea. The idea is just the following. So first of all, what I'm going to do is I'm going to first look at triples of points in the boundary, and I'm going to write parens here, shorthand for 3 distinct points, as opposed to, we need 3 distinct points. And I want to project this to x. All right? So what I'm going to define is a projection. Then I'm going to map this over here and project it here. And I'm going to try and use this. So first I have to tell you what these are, and then I'm going to try and use this to get the map here. All right? Okay, so what is this? Well, let's say I'm an x, and I've got 3 points, A, B, C. On the boundary. Well, I can join them by geodesics, by geodesics, like this. Okay, and then I can talk about a sort of a barycenter of this triangle. I can look at all things which are distant, say maybe 2 delta from all 3 sides. Look at that's some bounded set. So I look at some bounded set of points that are close to all 3 sides, and take its center, barycenter. All right. Well, okay. Again, there's not a unique geodesic here and here. I have to allow for all of them. But you look at a set of all points which are within 2 delta of all 3 sides of some ideal triangle from A to B to C. That's a bounded set. Take its barycenter. All right. So that's what this map is. All right. It picks out a barycenter in some appropriate sense of the word of ABC. All right. Okay. So that's my map, and I can do the same thing on Y, all right? So now, how do I get a map from here to here? Well, if my point was a barycenter, happened to be a barycenter, I could lift it, look at everything in the inverse image, push it over, and send it down, right? Well, okay, not every point is a barycenter, but every point, here's the co-compactness, is within a fixed bound, a uniform bound of a barycenter. And this is where co-compactness becomes important. So instead of looking at the inverse image, maybe the point I'm trying to lift here is not this, but this. So, but the point is, instead of just trying to lift Z, I lift some little ball around Z, which I know contains one of the barycenters, okay? And then I take I X inverse, I take F, and I take I Y, okay? That's no longer a single point. That's now a set, but what Paulin does is prove that this is bounded. This is bounded. Independent of everything, just depends on delta, and set F of Z equal to the barycenter. Center. Barycenter, whatever you call it, of this thing. Okay? All right, so that's the idea. Lift, push over, push down. And everything, all the arguments, you end up with bounded sets and you take their centers. That's how you define all of these things. Okay, and then of course you have to show that it's a quasi-isometry. I won't do this exactly, but let me just say approximately. I want to know if I have 2 things Z1, Z2, and I want to know the distance is not too badly distorted. Well, if I could find, some two triangles where these were close to the barycenters, if I could manage to do this and find an A, B, B, C, then I would know that what I'm looking at is very close, basically the distance between these is almost the cross ratio. So the idea is to approximate the distance between 2 points by a cross ratio, and then use the fact that cross ratios are preserved up to some bound. Okay, so that's the principle here. And this, by the way, is the part that's going to fall apart when we, this part's going to work nicely. This part's going to sort of be much more difficult if we get to our general case. All right, so that's all background. Let's see, do I need to tell you anything else about that? No, so let's move on. So this is the hyperbolic case that was done by Paulin and is well understood. All right. So now what we want to do is try to generalize this beyond hyperbolic groups. Right? So we first, so the main theorem I'm going to talk about today really applies to cat zero groups, but some of what I'm going to say works much more generally. So I want to tell you about these Morse boundaries. Actually, let's look at the cat zero case for a moment, because this is what motivated the whole thing. So cat zero case. Okay, so X is now cat zero proper. And eventually we'll have to require compact at some point, but not yet. All right, so we can still define boundary X the same way. I mean, the same definition I gave you before works perfectly nicely, and there's a nice topology and all that. But boundary X, as before, defined as before. But things start falling apart very quickly. So in particular, we don't even have the forward direction. It's not quasi-isometry invariant. A quasi-isometry of cat zero spaces does not necessarily induce a homeomorphism on the boundary, and this was this well-known example of Prof and Kleiner, a simple example of a right-angled Artin group, which could act geometrically on two cat zero spaces with different non-homeomorphic boundaries. All right? So defined as before, but not line. So even the forward direction of Paulin's theorem, the easy direction fails. All right. Sorry, that's not Paulin's theorem. It's just Gromov's theorem. It's just it fails right away. All right. Okay. So obviously it's not sensible to ask for the converse. Okay. So this is what motivated the work I did with Harold Sullivan. So
when you say it's not invariant, it's never your invariant or something.
oh no. There exists example. Sorry. Quasi-isometries need not induce homeomorphisms. There exist quasi-isometries between cat zero spaces that do not induce, that for which there is no homeomorphism on boundary. The boundaries are non-homeomorphic. That's all I'm saying. There exist quasi-isometric cat zero spaces which are not have non-homeomorphic boundaries. All right? Yes. Okay. All right. Okay. So yeah. Why? Let's say why. All right. What goes wrong if you look at the proof? The key reason is that the Morse property fails. In general, in cat zero spaces. Okay, so what's the Morse property? The Morse property, if you remember, says alpha is Morse if given any quasi-geodesic with endpoints on alpha, it stays bounded distance from alpha. Now the bound, of course, let's say n, actually depends on the quasiness. So this is a lambda epsilon quasi-geodesic. Then there's a bound depending on lambda and epsilon such that it stays. So it's not really Morse constant, it's really Morse function. So that's the Morse property, and that's key to proving quasi-isometry invariance in hyperbolic spaces, because the idea is you start with a geodesic ray and you hit it with your quasi-isometry, and what you get is a quasi-geodesic ray, and you want to straighten it. Well, straightening it requires that it stays bounded distance from a. I mean, you can't straighten in general if you don't have some kind of property like this. So this is sort of the key property that allows you to say that quasi-isometries induce homeomorphisms on the boundary. Okay, so with that in mind, and let me also say, in my work with Harold Sullivan, we thought about the following. Oh, let me just say, yeah, however, some geodesics in X in cat zero space may be Morse. That is, you can have some that are and some that aren't. Let's look at some examples. All right, it can fail, but it can also still hold for certain types of geodesics. So the easiest example, I mean, it's sort of trivially easy, but it's an easy one to think about, so let's do an easy example. Let's take X to be the universal cover of torus, wedge, a circle. T2 wedge, a circle. Okay? So we take its universal cover, and in the universal cover we see lots of flats, and then which I'll think of as being kind of horizontal, and then we see lifts of this at every lattice point, and then we see flats attached to those, and then we keep going, right? Okay. All right, so let's think of flats as being horizontal and the S1 parts as being vertical. All right, what is Morse and what isn't Morse? Well, it's not hard to see. Obviously, if something stays in a flat for an arbitrarily long time, it's not Morse. On that, things go to pieces quickly. But that as long, if we take any geodesic which spends a uniformly bounded amount of time in flats, those are all Morse. So you can spend, time, I don't care, long time, but some bounded amount of time, then you have to leave your flat. And then you can go for a while in another flat, and then you have to leave that one, et cetera, right? So you just can't ever settle down. You can't spend longer and longer and longer and longer in flats, all right? Okay, so Morse, so alpha is Morse. If and only if bounded time. And there are generalizations of this. You can write down criterion for any right angle argument, in fact, for any cat zero Q complex of which geodesics are Morse and which ones aren't. There's very concrete descriptions. Okay? And there are lots that are and lots that aren't. Okay. So, all right, and not only that, it turns out that, I'll write this as a theorem. This was in my paper with Harold Sultan, but parts of it was already done by Vestina Fujiwara. I think maybe some other people, a lot of bits of this were already known. We just sort of put it together all in one statement. It says, so X, again, is proper cat zero. Then the following equivalent. Alpha a geodesic, it can be a ray or a bi-infinite, I don't care. Then following equivalent. Alpha is Morse, meaning that there exists an n such that blah blah blah. No, I want to put it in the n. Let's put in the n. This is a function, the n Morse. Alpha is decontracting. And three triangles based on alpha are alpha thin. Okay, so let me tell you what all these means. And the reason I'm putting in the n, the d, and the alpha as part of the theorem is that these determine each other. If I know this, I can figure out this. If I know this, I can figure out this. These are determined by the constants are all determined by each other. All right, given one of these. All right, so what is this? N Morse you already know. Decontracting says that if I have any ball that doesn't intersect alpha and I project it, then the projection has diameter at most d. All right, for any ball whatsoever. And delta thin is what you think. I don't have room for it there. Delta thin means any triangle whose base lies on alpha is delta thin in the usual sense. Every point is within delta of one of the other sides. So if one side lies on alpha, then the triangle is delta thin. Okay? So the moral of this story is that in cat zero spaces, geodesics either look really very much like geodesics in hyperbolic space, or not at all like geodesics in hyperbolic space. But once you have one of these properties, you have all of them. In a cat
So
zero.
the n and n Morse is the amount of time it spends in flats, or?
No, yes, in this case, in this example, it would be the amount of time it spends in class. That's right. Well, no, it's the distance between, I don't know. It's determined by the amount of time it spends. I mean, it's the actual distance, how far away a how far away, yeah, it's the distance from, how bad the triangles can get in a flat. Right?
Okay.
So, the n is just, bounding how far away a quasi-geodesic can get from the geodesic. Yeah. Okay, so the moral, I'm not going to use these. Well, the delta fin I will. But the point here is that in cat zero spaces, at least, once you require something to be Morse, you have lots and lots of useful properties, and you can treat them as if they're geodesics in hyperbolic space, essentially. That almost all the kind of things you want to say about hyperbolic geodesics apply when you're working on that particular with that particular geodesic. Okay? Questions? Yeah.
Can you formulate it just in terms of the asymptotic? Just to say that something like
There is a formulation, yeah, there's a fourth condition that I didn't bother to put here, called lower divergence. And the divergence, of course, is very related to like cut points in asymptotic cones. And I think the answer is probably in the cube complex case you can. I'm not sure I would know how to do that completely generally. But there's a fourth condition that's equivalent to this about divergence, which is the one that would translate most easily to asymptotic cones. So I can tell you about that if you want, but I'm not going to use it here. So. Probably. I mean, there's,
I would guess in an asymptotic cone, you lose the quantitative information that you keep.
That's right. That's right. And in fact, the fourth condition, when we state the fourth condition in ours, we don't do a quantitative. It doesn't have a quantitative aspect. These three are quantitative, and that one isn't. All right. And quantitative is going to be extremely important here. All right. So I want to get to hopefully stating the theorem I want. All right. So first of all, this brings us to the definition of what's become known, what we originally called the contracting boundary, but has since become known as the Morse boundary for reasons I will explain. All right, so, okay, and the reason is that this makes sense for any geodesic proper geodesic. So for any, you don't even need cat zero anymore, proper geodesic vector space. Can define a boundary, what we call the Morse boundary. And this is the set of alpha is a Morse ray. So it's a ray with some Morse constant that satisfies some Morses and Morse for some n. All right, same equivalence relation, all right? So we're only going to allow the rays we like, and then throw out all the ones we don't. But it turned out to prove anything useful about this, we had to pick a slightly finer topology. That is, you could view this as a subspace of the ordinary boundary, at least in the cat zero case. But there's two problems there. One is my space may not be cat zero, so there may not even be a boundary. And secondly, the subspace topology turned out not to be the one we needed to prove things. So let's define the topology. So the topology is, I guess I am thinking of cat zero case here. But, all right, I'm going to wave my hands. It's defined as, the direct limit topology over the piece with fixed Morse Morse So we limit the n, we fix the n, and in the cat zero case, so I'm mostly interested in the cat zero case. In the cat zero case, we honestly take the subspace topology on this, but then we take the direct limit of all those. In the not cat zero case, you have to first define a topology on this, which you could do using Gromov products and blah, blah, blah. It's possible to define a topology on this, and then pass to the direct limit of all those. And again, in the cat zero case, if you don't want Morse, you could instead use D contracting here instead of N Morse, which is a little easier to think about because D at least is just a constant, whereas N is a function. So it's you know, you can use either one. It doesn't really make any difference here. Yeah.
But so it could be empty, even
It could
when
absolutely
there's some
be
negative
like the
curvature.
plane. It can absolutely be empty. Okay, but here's the key theorem. All right, so this was first, I originally did this, introduced this idea with Harold Sultan, and we did the cat zero case. So ours was we were only looking at the cat zero case. Then my student, Matt Brandeis, looked at the same question more generally, and it turned out the contracting condition wasn't good enough. You really needed the Morse condition when you went outside of the cat zero case, and we proved that for any proper geodesic metric spaces, a quasi-isometry, any quasi-isometry, X, Y, increases, and homomorphism. Okay, as Rick points out, these can be empty. All right, it's and by the way, of course, this means boundary G is well defined. It may be empty, but that's also well defined. And in fact, if two groups are quasi-isometric and one has an empty Morse boundary, then the other one has an empty Morse boundary. I mean, it says it's a well-defined object. It might be empty in some cases. Obviously, those aren't the interesting cases. So we're mostly interested in cases where there's at least one Morse boundary, and then you can show Morse geodesic, and then you can show there are actually lots. You move them around, and you get the lot. So sorry, at least two, then you move them around and get all tons of them. So the interesting cases are the cases where there's something interesting in here, where there's something reasonable in this boundary, something actually played. Okay, so that's the idea. I'm almost out of time and haven't even gotten to the theorem. Okay, so we define the Morse boundary, and our goal for the theorem I wanted to talk about. So we did that a couple of years ago, actually. And what I wanted to talk about today was we've been recently with another graduate student, Devin Murray, trying to do an analog of Paulin's theorem, which says that if I go the other way, so if I have a homeomorphism, when does it come from a quasi-isometry? And you need some condition, like quasi-mobius. All right, so let's. So the question is, is there a converse, a sort of converse in the sense of Paulin, all right? Okay, and here we really, so far anyway, only have this for cat zero, but I think it's a totally interesting and reasonable question of whether you could push it beyond cat zero, whether it works for, okay, not every geodesic metric, but some more general class. But in our case, we are only doing it for cat zero because we're very much using the equivalence of all the different conditions and applying projective stuff and delta fin, and we're using all the equivalences. So so here's the theorem. Let me state the theorem, and this is with Devin Murray. So x, y, proper cat zero spaces. And I need compact, proper, co-compact in the sense of before that there's some co-compatibility. And then we also want to assume boundary x, boundary y containing at least, well, we probably need stability, but yeah, at least 3 points is good enough. The stick points, all right, so we need 9, not too stupid. Okay, so then,
So the Morse boundary.
the Morse boundary, yes, absolutely. Sorry, the Morse boundary contains at least 3 points. Then let F, capital F mapping, boundary, M, homeomorphism, and the following are equivalent. Quasi-isometry. And 2, well, it's not exactly the same as before. F is quasi-mobius. And I need another condition for me. I probably don't, but quasi-mobius and 2-stable. Okay, so let me talk about these. 2-stable. Yeah, so, let's put this up here. Okay, definitions. Some definitions or ideas behind this. The first is, let's see. All right, first, cross ratios. I claim we can define them as before. What did I want to say about cross ratios? Oh, yeah. So there was this question, about projections, right? So we wanted to just define it. Before we just defined it by taking projections, right? And defining as distance between the projections. Remember that? And we said, well, the projection's not really unique. It's just really some bounded set. You take its polycentric. Well, we need the contractingness of this to get the fact that projections are well defined. All right. So it wouldn't even be true if we took an arbitrary geodesic here. So cross ratios, alpha contracting. So let's call this alpha alpha contracting implies projections pi alpha of some point say B, well defined, can be defined. All right. Now, I should say how contracting it is determines how well defined it. How much you have to do. All right. So you're always having to control your contracting constant, and that's why the direct limit topology is so. Did I forget M? I keep forgetting to put an M in here. Sorry. All of these should be M's. We're now working entirely in the Morse boundary. So the reason you want the direct limit topology is you prove things for a fixed constant, a fixed Morse or fixed contracting constant, and then it just passes easily to the direct limit. You prove it's true for any fixed constant. So what we do is we look at only things in which everything's decontracting, we make it work there, and then we pass to the direct limit. That's how this whole operation works. So the first thing is that we can define this, so we can define the cross ratio as before. As the bottom. No change. We can do exactly what we did before, just define it in terms of these projections. So the second is what do we mean by quasi-mobius, and this is actually different. So define F to quasi-mobius if there exists if for each well, n, again, I like to think in contracting constants better, because they're just constants instead of, yeah, let's go. Well, no, each n, there's this function. Sorry, n. Infinity. Zero, infinity. So the amount by which it distorts can also depend on n, right? So, such that. Okay. For all. For what? Well, for all, A, B, C, D, oh, I didn't introduce this notation. All A, B, C, D for which any two, the geodesic joining any two is n Morse. All right, so you look at sets of 4 points where if I join any two to each other, it's an n Morse, it's got a fixed Morse constant or a fixed contracting constant, all right? I write it like this, boundary m x for n in 4 points, distinct points, connecting any two is n Morse. So you want to bound all the Morse constants simultaneously. That's the key. All right. All right. So quasi-mobius isn't quite the same as it was before because now it gets to change as we change the Morse constant. All right. All right. And the last thing is, yes, I know I'm out of time. What is too stable? Well, because we have to bound the Morse constants, it's really important that this function take things in here to things in here with some bounded Morse constant. Doesn't have to be the same one, but there has to exist an n prime such that this maps into the corresponding. So f is too stable if f of boundary. If for all n, there exists n prime such that f maps, actually, f takes n Morse. I can't say that. Let's just say it this way. F of the 4 really doesn't matter. You could just do 2 here. It just has to take each n Morse geodesic to an n prime Morse geodesic. It's really all. I mean, each pair of points joined by an n Morse geodesic has to go to a pair of points joined by an n prime Morse geodesic. Now, there's some control on how they add. So what are you doing? You're taking, sorry, I'm rushing here, taking x, and I have 2 points that have a nice geodesic between them. I want to make sure they go to 2 points that have a reasonably nice geodesic. And at first we thought that was going to be automatic. Turns out it's not. We have counterexamples. There are homeomorphisms for which that is not the case. But we conjecture none of these homeomorphisms are quasi-mobius. So conjecture F homeomorphism and quasi-mobius because F is too stable. We think this is not necessary. We think there's a good chance this extra condition is not necessary because all the counterexamples we were able to construct of homeomorphisms which are not too stable were also not quasi-mobius. We think they may be unnecessary. That's our condition. All right, so I'll just end. I'm out of time. So that's the theorem. The first part of the theorem, the construction of the map on the interior, is pretty much it's a little messier, but it's pretty much what Paulin did. But the second part is actually trickier for a very simple reason. So the second part was, well, supposing we can find something that's close. I have 2 points, and we suppose I can find something like this and just use the cross ratio. Well, the problem is these 2 points could be hugely far apart in some flat, and then this geodesic is going to have a terrible, terrible, terrible Morse constant, and you have to be more careful. You can't quite just say, do what Paulin did. You have to be a lot more careful, and you use the fact that there's this group action, and it just takes a little more work, but it's doable. It still goes through. You just have to be more careful. So that's it, and it would be really cool to know whether, first of all, this could be generalized beyond just cat zero, and also one could ask whether this quasi-conformalness could be generalized, and that has other problems. But I think if anybody's interested, I can talk about that. Sorry.
Do you know if the group, three-dimensional group Sol has a non-empty Morse boundary?
I don't know. Does anybody know if it has any contracting geodesics?
They're so crazy.
I would guess not,
No.
but I did.
Yeah, I would
Yes,
guess
no.
not too. I
Um,
wouldn't swear by it.
would guess not, but I don't know.
Do you have any counterexamples where you get rid of this funny, and I mean, you have this more complicated notion of quasi-mobius. Do you have any homomorphisms
Oh, that's,
which are
you
not
mean which are
traditionally
better than that?
quasi-mobius?
I mean, they
but
could be better than that, I guess. You
What-
mean, and then what? You want to say something stronger?
yeah, what I mean is suppose you have a.
Oh, I
homomorphism.
see.
So
In the forward
You'd like
direction.
to eliminate this.
In the forward direction,
Yeah,
right?
the weird
Proving that
condition
if,
about you want to get rid of psi sub n, you just want
No,
to
probably not. Okay, here's interesting. So Devin Murray studied just general properties of Morse boundaries of cat zero spaces in his thesis. And basically, he found that any time they're nicely behaved, it's because your space turns out to be hyperbolic. It's basically there's a bound on all the Morse constants, right? So the Morse boundary is compact if and only if the space is hyperbolic. The Morse boundary is the tricycle if and only if the space is
Right.
hyperbolic. The Morse boundary, so my guess is, if I had to guess, you're going to find that it was actually quasi-mobius, that there's one that works for everything if and only if
Oh, I see.
the space is hyperbolic. I'm guessing. I don't have a proof of that.
I mean,
but
I
bet you
understand
anything
that,
that's what's
the
gonna happen.
end and the end Morse is going to be bad if it's not hyperbolic, but you might, okay.
I'm just
Okay.
guessing that it's going to get where that it's possible that you could have it still. You just want this function to work for everything, right? Not to
Yeah.
depend on n. Maybe.
Yeah, so in other words, if you had one that worked for the more complicated definition, it would also work for just one.
So maybe a weaker thing to ask for is, and I'll ask it in your contracting definition because then I know what to say because
Yeah,
it's one
contract
number.
is better.
Right,
Contract
right,
is
like,
better. I shouldn't use
could it be that, the contracting constant, call it D, whatever it is, that the other D prime that you need is at least, uniform, like,
Yes.
D prime as a function of D is, say, 2D.
Oh, no, you have some control.
You have some-
you
it
can,
is
oh, I see.
quasi-mobius
Not,
then.
not if you have a quasi-isometry, then you have some control.
Yeah, I would think that would then be,
So here's the problem, and here's where the two stable comes in. It's really weird. In fact, we didn't realize we were using it at first. We thought it was automatically true, and then we realized that it's more subtle than that. Because when you talk about the contracting constant, to even define the boundary, you have to set a base point. Because otherwise, if you go to a different base point, you get a different contracting constant, because maybe this part's really badly contracted. To talk even about what you mean by this part of the boundary, right, you've got to set a base point, all right? So the problem is you can have things, where this is, so if it's a homeomorphism, then this will go into some D prime, this will go into this. No extra conditions needed. In order to be a homeomorphism, these have to, because of the way the topology is defined, this will have to go into this. With respect to some fixed base point. So this is really, I really fixed a base point here. So with respect to a fixed base point, there will be a D prime such that this goes into this, all right? But the problem is that we can have two decontracting things here, which when we connect them here, we can have something that's decontracting here, but is hugely badly contracting when you base it at this base point. You have to travel through an enormous amount of the flat before you get to it, all right? So this contracting of the bi-infinite geodesic has, once you fix a base point, can have very little to do with the contractingness based at the point. And because these are actually defined in terms of base points, you lose track. You can't hold on to it, it turns out, without. You really need to work with these for this theorem. And you just can't get back from, you can't get back from the contractingness at the base point versus the contractingness at that. So I don't know, go back to your question again. Maybe I'm not answering your question.
I'm not sure I asked the right question. There's just, I mean, in the right reason I'm asking the question, maybe also the reason Rich is asking the question is, the thing we like to do with Paulin's theorem, or many people like to do with Paulin's theorem, is if you have a group quasi-isometric to a space,
And they
then the
ask.
group acts on the boundary of the space by uniformly quasi-mobius maps, in some sense of uniformly quasi-mobius. That in the classical setting, in the hyperbolic setting, it's very easy to, I mean uniformly quasi-mobius. There's a quasi-mobius constant that's fixed, or quasi-mobius function that's fixed for all group elements. And here you don't even have, for one group element, you don't even have a fixed quasi-mobius function on the entire boundary.
No, but it could work for each D. Yes, you do. Fix your D. So you only care about the D contracting part. So I bet you do. I bet you can do this. That for fixed D, for a given D, all the group elements can use the same quasi-mobius function.
So in this
I think you could say that. I think you
Okay.
could make it uniform, but it's uniform for each
stratum.
for each strata.
Are the strata ever, like an example, are the strata nice connected spaces, or are they messy spaces?
Well, they can be. You can get either one. So, for example, for right-angled organ groups, for each strata, it's a Cantor set. So, get a correct limit of Cantor sets. All right. But on the other hand, if it has some hyperbolic stuff in it, I mean, I've got right-angled Coxer groups with nice circle, hyperbolic planes in them, and they're going to be fine, and they're going to show up in the, I mean, I can construct either kind of examples. Yeah. In general, the topology on the direct limit is pretty much of a mess, but the topology on the fixed pieces, on the decontracting parts, can be very reasonable. It's compact, it's metrizable, and since most of the proofs work at that level, you really aren't confronted with this horrible topology.
Yeah. Have you ever tried to eliminate the base point and just take for each point at the boundary the best possible rate and use the
Yeah, we did think about this. We were trying to put measures on these at one point, and we were doing an infimum over the. I haven't tried redefining the topology. It's an interesting question. We did think about that for a while. I've forgotten now what we ran into with that. There were some issues, but it's an interesting. It's actually probably worth thinking about some more. That question.
Well, it was just occurred to me that we've reached the stage where not even the questioners can understand the question. In some of these spaces, like I guess like in the for like this symmetric space for SL3, that the boundary's empty because the geodesic. But you could imagine that like you had a tube of quasi-geodesics that went around one, and a lot of them would be sort of Morse in a lot of directions.
It went around.
Well, no, if you have a geodesic in some symmetric space, say that has some hyperbolic directions, then a lot of the geodesics a lot of the quasi-geodesics are sort of cling to it. Just not all of them.
Here's a question
You see what I'm saying?
It connects to Rich's question. There is a definition in the symmetric space and building setting of a Morse quasi-geodesic. I've asked this of several people who think about your boundaries. They have a definition of a Morse quasi-geodesic, which is really the Morse quasi-geodesics are the ones you can control at infinity in the way Rich is describing. And they use this to control certain maps. But it feels to me like there should be some common generalization of your use of the word Morse and their use of the word Morse.
Yeah.
'Cause-
I'm not familiar with this.
Kind of Morse on average in a sense. Like a lot of the quasi-geodesics sort of have to stay close. Some are bad, but a lot of them do. And you could probably extract information. If you had a quasi-isometry.
To at least to generalize this boundary to
to
I mean,
to make it bigger. Yeah.
Yeah. Well,
More
we did.
relaxed in a way.
We did try. We did try asking what if we allowed things that didn't, it spent longer and longer. I mean, we did try various generalizations, and in each case that we tried, we could find a counterexample to show that it was not quasi-isometry invariant anymore. And since that was our first,
Yeah, no, for sure,
that was our sort of fundamental starting point, was to get something that was quasi-isometry invariant. So far, we haven't found a general, but still, it's kind of amazing that this works for any geodesic metric space. So, and I think this converse will work for some class. I don't know what you mean exactly. We used everything we knew about cat zero, but a lot of it, I'm sure it could be generalized.
But I was thinking like the Ricci curvature. If you go along a geodesics, it's sort of like telling the growth of an area growth of a cross section or something. And so like a negative sectional curvature, that talks about the divergence of geodesics. But like the Ricci curvature is talking about like the geodesics of a tube around. So this is the kind of thing I was thinking about.
All right, I'll have to talk about this. Yeah, I don't know
Okay,
anything
all
about this.
right.
Yeah, sounds interesting.
Thanks.